Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston, we don't have a problem. We're going to discuss a kind of a difficult topic called equilibrium. So when we're talking about forces, right, we learn about forces, that when you are in a state of, well, let's back up. If I have a free body diagram where I've got an unbalanced forces, let's say I got a force here and a force here, and that's all, then that object will accelerate, right? But in an equilibrium problem, the object is not accelerating. So what that means is that the total sum of the forces is equal to 0. Or, the way we would say that, is the sum of the forces is equal to 0. Now, when you're doing these problems, one thing that you're going to discover is it's much, much easier to not just think of the total sum of the forces as 0, but that means that the sum of the forces in the x direction are equal to 0, and the sum of the forces in the y direction are equal to 0, and the z direction, if you really want to get there. Remember, this big funny-looking e means sum of, because you're going to want to break it down into both the x's and the y's when you're solving these equilibrium problems, right? So one quick example, if I have an object right here that has a weight, it's on the ground or something like that, it's got let's say it's got a force of 1,500 newtons, but if it's at equilibrium, for this to happen, it must have a opposing force of 1,500 newtons. This would probably be the normal force, right? If this is an object that weighs this, it's a box sitting on the ground that weighs 1,500 newtons. Remember, weight is measured in newtons. Then, of course, the ground is pushing back up with 1,500 newtons because it's not accelerating. Now, when I say not accelerating, something could be moving with constant velocity. That's not accelerating. So this object could actually be moving to the right, possibly, but it's not accelerating, though. Remember, forces cause acceleration. They don't cause velocity. All right. Now, this looks relatively easy, but it can get complex. So let's do a bit more of a difficult problem. Let's say that I have a hammock. So let's try to think this problem. We got a hammock. Okay. And we've got a person who is sitting here laying in their hammock, right? And it's attached by 2 ropes, right? At different angles, okay? And this right here is a 40-degree angle between hammock and it's hooked up to a tree or something like that. And this is a 20-degree angle, right? And the person has a weight, and we can figure out what their weight is. That's just, the force of gravity is m times g, right? And the question, and then what's happening here is they're going back here at an angle, and what's holding together, we're going to call T, the tension in the rope. And we'll call this the TL for the left tension, and this the TR. And the question is, what is the tension in the left rope, and what is the tension in the right rope? All right, so let's draw this in an easier free body diagram. We have, and let's say we know the mass of the person is 100 kilograms to make our life easier. And so, and I'm going to round numbers here. We're going to say that then the force down is 1,000 newtons. 100 times 9.8, I'm going to round 9.8 to 10, will be 1,000 Newton force down. And then I want to draw this ish at a 40-degree angle, where this is 40 degrees. And this is T right. I'm going to draw this at a 20-degree angle. All right. And this is T left. So that is my free body diagram. And the question is, what are the tensions in the left and in the right? So what you want to do is, remember, because the person's not moving, they're not accelerating, the sum of the forces equals 0. That's the key thing. But we have to break it down into the sum of the x forces and the sum of the y forces, because we have to play some SOHCAHTOA games to solve this problem. Make sense? So let's figure out how we're going to do this. So if we were to break this down, right, the left side, let's say, it is the sum of both the leftward force this way and the rightward force this way. And so let's deal with the sum of the forces in the x direction, that's 0. The sum of the forces in the y direction, that's 0. But I want to find what the tensions are on these two ropes. It's going to turn out it's going to be kind of a two equations with two unknowns kind of a problem is what it's going to be. So let's work this out. So in the x direction, the TL would be in, and this is going to be the adjacent and the hypotenuse. So remember, we've got so, ka, toa, and actually we're just going to deal with the so's and the ka's. So the adjacent over the hypotenuse, the cosine. So the for the left, we could say that the cosine of 20 degrees is equal to, we're going to call this fxl for the f of the x in the x direction in the leftward times over t of the L, right? Or to find the fxl, we can say TL cos 20 equals the fxl. Does that make sense? And then the opposite's going to be true. As a note, this will be a negative number, right? Because it's in the negative x direction. On this one, for the right, you'll say TR cos 40, right, equals FXR. Because if you think about it, FXR minus FXL has to be equal to 0, right? So I can make an equation now, right? And so I'm just going to write it out this way, and then in terms of TR and TL, right? I can say T in the right direction times the cosine of 40, I'll just do it this way, plus minus TL cos 20 equals 0. So that's equation 1. But you might notice we got TR and TL, and that's two variables I can't solve the problem. So now we can play the game in the up and down version, right? So the weight is only going down. So I can now, on this side, the sum of the y's have to add up to 0. So I can say that 1,000 newtons, right, 1,000 newtons, that's the force down, is going to be equal to the forces up. And the forces up here are going to be the whole sine thing, because these are the opposite angles. So that's going to be equal to TR, instead of cosine, sine, not plus, this would be equals, they're equal. TR sine 20, and this is also going up, plus T, not R, that's not R. This would be TL sine 20, TR sine 40 degrees. Now, you notice now we have an equation here, we have an equation here, and we want to try and solve for the L and the R. And so when I know this is equal to 0, they basically have to equal each other, so I can say TR cos 40 equals TL cos 20. Now I have to substitute, so let's think about our algebra. I'm going to divide both sides by, say, cos 20. And these cancel, so TL is this. So I'm going to plug this in to here, so I can say 1,000 equals TL is TR cos 40 over cos 20 times sine 20. And if you want to put these all into numbers, you can, plus TR sine 40. Now I'm just going to do some algebra here on my calculator. So I'm going to say cos, let's get some numbers here. Cos of 40 times sine of 20 divided by cos of 20 gives me 0.27. So this then is 0.28 actually TR plus, and the sine of 40 is 0.642. So that'll be 0.642 TR, and that's equals 1,000 newtons. Got it? And now what I want to do is it's going to add the same. It's like this is x and x, so you 0.28x and 0.642x. So I say plus 0.28. That comes out to 0.92 TR equals 1,000. Divide both sides by 0.92. Those cancel. And I get the T, now which one's this? The R is equal to 1,086 newtons. So once I know the TR is 1,086, how do I find the TL? We figured that out over here. We said TL is this. So I just take TR, which is 1,086, times cosine of 40 divided by cosine, oops, I didn't do that right, 1,086 times cosine of 40, close parentheses, divided by cosine of 20, close parentheses. And I get T L to be 885 newtons. So the right side has a tension of 1086, and the left side is 885. And that makes sense because this one is, it's a steeper angle, so it's going to hold more of the weight than will this one. So you can see, look at this board. It's crazy full of all kinds of problems. This is how you do these problems. It's all about coming back to the fact that the sum in the x and the sum in the y are equal to 0. And then there's a lot of numbers to deal with. Houston, we don't have a problem.